All right, the third speaker this morning is A Minahan on finite size effects for giant magnons.
So I'd like to thank the organizers for inviting me to give this talk, and also for organizing such a nice meeting. As Matthias said, the title of my talk is Finite Size Effects for Giant Magnons on Physical Strings. And this is work done in collaboration with Olaf Olsson-Sachs, who is a pretty new graduate student at Uppsala. Let me just start off with some introductory remarks. So there have been, of course, many exciting results over the last year or so for the infinite J or S limit. I guess it's now 2 years. So I guess in a sense this really all started with the asymptotic beta equations first introduced by in certain sectors by our chairman, and then generalized to the full ADS5 cross S5 by Beizert and Staudacher. And there have been many other things, not necessarily in this order. There have been the discovery of the giant magnons by Hoffman and Maldacena and Dori and others. And then, of course, there's the realization about how to centrally extend this SU2/2 squared algebra, and from that determine the S matrix by using crossing symmetry and using this Ionic equation, finding solutions to this by BHL and BES. Then there has also been the Beizert-Eden equation, the Beizert-Eden-Staudacher equations, which we've heard a lot about this week. And along with their equations, there have been various solutions or partial solutions, either numerically. What's so funny? What's that? That sounds funny saying the whole thing, yeah. You know you made it when it's just your initials. So anyways, then there's the solutions, BES themselves, and Bennett et al., Alde et al., and Basso et al., which we've heard Basso's talk today. And of course, then there's also been many different field theory and string theory checks, and this is by lots of people. Now, these are all in the infinite J limit, or infinite S, but there's also been progress at finite size. You keep laughing, I'm worried.
That's a good citation, lots of people.
Yeah. Okay, so there's been also some progress at finite size. So there's been the interesting results of Ambjorn, Yannick, and Christensen showing that wrapping effects will show up at basically at order 2J in the string couple, ordered, G to the 2J order. And then there have been calculations of the finite size corrections to giant magnons by Ayatollah Frolov and Zamoklar. Also, there have been finite size corrections for spinning strings, by Schaefer, Nameki, Zamoklar, and Zarembo. And then there's also been these recent calculations of finite size corrections starting from the S matrix by Yannick and Lukowski. So I'm going to concentrate on finite size effects, and and only finite size effects for giant magnons. And so the previous results have been on the case where the classical charge of the giant magnons is 0. They're fermion 0 mode, so they really have charge 1, but classically we assume that their charge is 0. And what I want to ask is, well, can we generalize this? In particular, can we find results for what I call physical strings, where basically the total momentum of these giant magnons is an integer times 2 pi. Now I wouldn't ask this question if I didn't think we could answer it here. So the answer is, I believe, yes. And what I will use today are some, I won't say ancient, but 2004 seems a long time ago, but old methods to sort of find these results. And actually, some of the results are actually quite simple that we find. So I'll give a brief introduction, and then I'll talk about doing calculations with finite gap equations. And then from these finite gap equations, I will do these computations for these finite size effects namely for the case first, where Q is not equal to 0, so these bound states of magnons discovered by Nick, and then also the case where we have more than one giant magnon present, so 1, 2, or whatever. And then what I'm going to do is I'll do some checks on the case where Q is not equal to 0. And basically what we can do is we can continue back. If we make Q very large, okay, we can sort of continue back to the Heisenberg regime, okay, and basically find the same sort of calculations, basically using the beta onsets. And then I'll just describe one check that we can do in this TBA analysis, although we don't have full results there yet. And then I'll conclude. So, okay, I'm sure you all know this, but let me just say it anyways. So, okay, we know we have the ADS-CFT correspondence, which basically says that n equals 4 super Yang-Mills is equivalent to type 2b on ADS 5 cross S5. And the size of this ADS 5 cross S5 is basically proportional to the 't Hooft coupling to the 1/4 power. And the dictionary, of course, is that the dimensions of the gauge invariant operators in the n equals 4 theory are equal to the energies of corresponding string states in the dual theory. So we, of course, always consider the planar limit. Okay, so in this case, we only need to worry about single trace operators. And in this limit, of course, we have this map from these single trace operators into spin chains. Okay, so of course, we can think of so one such operator is trace z to the j. This is a chiral primary. Okay, so it's a protected operator. And so we usually think of this as the spin chain ground state. And then, okay, it's the usual story. Okay, the operators then, the other operators, okay, we have, say, a bunch of z's. And we sprinkle in these other types of operators inside these chi-i's. These chi-i's come in 16 different flavors. 8 are bosons, 8 are fermions. Okay, so we have this sort of picture. So I'm basically just going to concentrate on the SU2 sector today. This is sufficient for what I want to do. Okay, so at the one loop level, okay, the anomalous dimension then is basically we can map to the energy levels of a Heisenberg spin chain, which is ferromagnetic. Okay, we will consider the case where we have Q impurities, or magnons, or down spins, okay, in this case. And of course, it's well known that in this case, what we end up with to find the energy levels, the different energy states of the system, is we solve the beta equations. Where e to the I p of the jth magnon to the j plus q. So j plus q is basically the length of this chain. I'll keep writing it in this notation today. And is equal to a product over the inverse S matrices of all the other magnons. Okay, so this is basically just the quantization condition for the momentum. Okay, so of course it's convenient to write this in terms of rapidity variables. So e to the I pj is equal to uj plus I over 2. Divided by uj minus I over 2. And so in this term, okay, this S matrix has this very simple form. Okay, and so we have this is this e to the I times the momentum to the length of the chain is equal to this product of these S matrices. And so this solves the solving this equation, we find the momentum. The momentum then are related to the energy through this dispersion relation. Where the energy for each magnon is 2g squared over, okay, this is probably hard to read. This light is dark here. So 1 over uj squared plus a quarter, okay. And I'm using, okay, there's many different, so there's been at least three different types of definitions for g. Okay, I'm using the one, so this is Nicholas's 2006 definition. So it's g squared is lambda over 16 pi squared. So, okay, so if we now assume that the numbers of j's, which are the number of z particles, and the number of q's are both very large, and let's assume that j is much bigger than q, okay, then we can take these equations, okay, and we can take a log on both sides of the equations, okay, and we basically get this approximate equation right here, that q plus j divided by uj times this 2i, 1 over uj minus uk plus 2 pi times ni, where n comes about because we have to choose a branch of the log when we take this. We have to choose the branch of the log we're choosing there. Okay, so one technique then for solving this is to turn this equation that involves a sum into an integral equation. So we can define a density, rho of x, which is basically a sum over delta functions of x minus uk, where uk are the positions of the magnons in rapidity space. And then that equation that we had from the beta equations becomes this integral equation where we have an integral over this density divided by x minus x prime is equal to q plus j divided by x minus 2 pi times an integer. And then the various so if we solve this integral equation then, okay, we can go back then and find the various quantities in our system, okay, namely q, the energy, the momentum. Okay, so the q, charge q is just the integral of this density, this integral of the density over the domain in which the density has support. And that's equal to q, but I'm going to write it in this funny way, okay, where I'm basically adding and subtracting j and dividing by 2 and splitting up q into 2 parts for reasons that will be clear in a little bit. The momentum then is found just by integrating this density divided by x prime. So you get a sum of pj is equal to p. And this p has to be equal to 0 mod 2 pi in order for us to consider gauge invariant operators, because we have a trace. The trace basically means that it has to be invariant if you shift each operator over by one site, which basically means the momentum has to satisfy this equation. And then the energy, okay, is okay, I'm considering the full energy, not just the anomalous dimension. So the bare dimension is j plus q. It's the number of bosonic fields, okay, plus this anomalous dimension part here. Okay, so then this integral, to get the energy then from this density, okay, it's this integral of rho x prime divided by x prime squared, and that's equal to 1 over g squared times e minus j minus q over 2. So it turns out then that solutions for these integral equations, okay, are basically correspond to solutions of the Landau-Lifshitz equation, which is basically the classical limit of the Heisenberg spin chain. Okay, so a general solution to these integral equations then is basically what is known as what we call a finite gap. So the solutions are basically determined by a series of cuts in the complex plane. So the complex plane is the rapidity plane, and we can have, say, n cuts, and along these cuts we have square root branch points. Okay, and the cuts correspond to where the density this density of the roots has finite support or non-zero support, and these different cuts correspond to choosing different values of n, the little n. Remember, little n corresponds to choosing a branch on the log from the log cut. All right, so since these are square root branch cuts, in general, then the solutions, the surface, then we're cutting the surface, will correspond to a genus n minus 1 hyperelliptic surface. It's hyperelliptic because we just have two sheets. Okay, and in general, then our solutions will be hyperelliptic functions. All right, so the way you usually tackle this problem is you define a resolvent. Okay, the resolvent is basically just the integral of the density divided by x minus x prime. Okay, now this x doesn't live on where these cuts live. Okay, but have an x out here, and you can then define two types of cycles on this surface. So you have A cycles, which sort of integrate around these cuts. Okay, and it turns out that this integral of this resolvent is 0 around the cuts. And then there are B cycles that go between cuts like this. So if we have a B cycle, so this crosses this branch cut here, so it goes onto the other sheet, okay, and then it crosses this branch cut here, and so it goes back onto the original sheet, okay, and comes around like this. And the integrals of the resolvent around these cycles will be 2 pi times an integer n1 minus n2, and the n1 and the n2 correspond to the log cut that we choose that these different branches live on. Okay, so that's sort of the general sort of solution for that. Okay, now we can recut this surface, okay, because this is a hyperelliptic surface. We can choose our branches to be different. Okay, so we can, instead of having, say, a branch cut that went between here and here, okay, we can put the branch cut between these 2 points here. Okay, but in order to do that, in order to keep the integrals of the cycles the same, we have to introduce what's known as a log cut between these two. Okay, and basically this recutting the surface is just an SPN -1 transformation of our hyper surface. And along these log cuts, okay, what basically happens is we put in a density, okay, which is constant along this cut. Okay. So it's basically what this corresponds to then is we have beta roots that are separated by an integer times I, or sometimes along this cut, or I should say a fraction of an integer times I. Okay, now let's suppose now I take the limit that j goes to infinity in this case. Then what happens then is that and let's just concentrate on just one of these things here. Okay, if I take that limit, okay, should be a singular limit of my surface, and so I'd expect my surface to degenerate. Okay, and indeed what happens is that this branch point here, which I call B, okay, will approach this branch point here A, okay, and likewise these two, and this one is A star is the complex conjugate of A, and B star is the complex conjugate of B. These guys approach each other. And basically, at the end of the day, when j goes to infinity, all I'm left with is this log cut that goes between them. Okay? So if rho x is equal to minus I, okay, this is basically corresponds to the case of a single, giant magnon in the string case. I'm still talking about the Heisenberg case here. And I could also consider the case where rho x is equal to minus an integer times I, in which case, then, this would correspond to having multiple magnons, okay, giant magnons, with the same momentum. So then it's very simple to compute what these charges are, because rho is a constant. Okay, so this integral of dx rho of x is, which gives me the charge q, so this is the bound state of these guys. It's just minus I times a minus a star. Okay, and the momentum p is dx rho of x over x, which is minus I log times a divided by a star. And then the energy E minus J minus K is just this integral, but since this is just a constant, it's trivial to do. Okay, and it's just given by this. Okay, so basically then just by just given A, okay, I know the Q, I know P, and so I know the momentum of the magnon, and I know the energy for the magnon. Okay, so so translating this back then, this A is equal to the charge over 2 times e to the IP times the cosecant of pi p over 2, and then E minus J, if I plug this in, turns out to be Q plus 8g squared sine squared p over 2 divided by Q. Okay, and you notice that that's the first term in the expansion of this square root here. So anyways, what does this correspond to in the classical solution? Remember I said that these things come from Landau-Lifshitz models. Well, this turns out to be what's basically a soliton that was first discussed by Lakshmanan, Takhtajan, and Fogarty around actually Fogarty I think is a year later, but around 1978. Okay, and the way you can think of it is that you have these spins that are all lined up, okay, and then there's some point along the spins where they start rotating. Okay, so they start rotating, go down like this, and in general they have some velocity, so they're moving along in one particular direction. And these are what what are now called giant magnons are. Okay, so what's the picture in string theory? Well, okay, these are the giant, so in the string theory picture, so if we now consider that case, well, these are the giant magnons of Hofmann and Maldacena, or if we have Q not equal to 0, okay, these are what are known as dionic giant magnons. Okay, Nick, I have to say I hate that name. But I don't have a good name, but I don't like dionic. So these are these dionic giant magnons, because dionic sounds like there's magnetic charge and electric charge. That's why I don't like it. But Yeah, I know, but maybe you should have used an I and not a Y. Or no, bionic doesn't sound good either. Okay, so anyways, back to the story. These we can sort of derive these in the same sort of way. Okay, now what we'd have is we'd start with a sigma model on R cross S3. Okay, with Virasoro constraints. Okay, and this will basically roughly correspond to being in this SU2 sector. And again, I won't go into the derivation about how we get this, but it turns out that you end up with another set of integral equations that are very close to what you had in the case of the Heisenberg magnet. Okay, so you have, I think this is missing a 2 here. This should have a 2. 2 times this integral over this density divided by x minus x prime. In the case of the Heisenberg magnet, this was j plus q divided by x. Okay, so this gets modified. Instead of having the j plus q, this is now the total energy. And the branch point, okay, gets split. Sorry, not the branch point. The pole gets split into 2 poles. Okay, one at x equals g and one that equals x equals minus g. But again, we have this minus 2 pi n. Then the integral of dx rho x prime, okay, instead of having, remember we had a j plus q term here, that gets replaced by an e. Okay, and then the rest of the integrals are the same thing we had before. Okay, so that's the only difference, is just change this term and change this term. Minor little change. Okay, well, of course, it has big effects. But so then again, you do the same story. Okay, you take j goes to infinity limit. Okay, it's done by Alan Terzu and Arkady and myself, and also by Vicedo. And in this case, then instead of, we have the same sorts of equations, but before this was just q was equal to this. Now this becomes e minus j plus q is equal to this combination. P is equal to minus I log a over a star. Okay, and e minus j, okay, is now actually the square root of q squared plus 16g squared sine squared p over 2. And I'll call this em for magnon energy. Pardon me? This is, I'm just looking at one particular magnon. I'll come to that. So this is just for one. Okay, if I have other magnons around, okay, they'll also have the same sorts of equations. Okay, so the total p has to be 0. I'll come to that point. Okay, so I want to think about the e minus, the corrections when j is very large but finite. Okay, so the q equals 0 case that was analyzed by Gleb and Sergey and Maria last year. Okay, and doing light cone, doing string theory on the light cone, and they found that this change in the e minus j, okay, is given by this expression here, minus 4g sine cube p over 2 divided by e squared times this exponent of minus 2j divided by 4g sine p over 2. And you notice that when q is equal to 0, this term here is just the energy of the magnon. Okay, so so you might ask, well, what is delta e minus j if q is not equal to 0? Okay, so what would happen also, what happens if q gets much greater than g? Okay, so then I approach the Heisenberg. And then we might also ask, how does the presence of the other giant magnons affect the result? And as Sergey was pointing out, I need to have p equal to 0 mod 2 pi. So it means on a physical string, okay, I need to have at least 2 giant magnons, or at least something else besides a giant magnon, that so that the total momentum is 0 mod 2 pi. Then you could ask, how does one see the quantization of the giant magnon momenta, and how do the results of these recent results of Janek and Lukowski generalize to this? Okay, so let's suppose now I have a bunch of giant magnons, okay, in the finite, where j is now finite. So instead of just having these log cuts, what I'm going to end up with are log cuts with little tails on them, okay, and these little tails are square root branch cuts on the ends of these magnons. Okay, so in general then, you can see that for each of these cuts, okay, for each giant magnon then, I'm introducing 2 cuts. Okay, so in general, every time I put in a giant magnon, I'm increasing the genus of my hyperelliptic surface by 2. Okay? So in particular, remember that the AFZ results, they not only gave results just not for the leading order, but several leading orders. Okay, and they expressed the results in terms of elliptic integrals. Okay, and well, they had elliptic integrals because they have just one giant magnon, so there's 2 cuts. Okay, so you expect elliptic integrals. All right, but J, I'm going to assume, is very large. Okay, so elliptic integrals, I can't even remember the difference, which one is K and which one is E. So hyperelliptic integral functions are even worse. Okay, so I'm just going to look for the leading order corrections right now. And so the leading order corrections, if J is very large, even though I have these square root branch cuts, I can at least assume that they're very short. Okay, so let's suppose then I look at, so the integral along this particular cut here, A and B, okay, what sort of integral equation will it solve? Okay, so I have an integral of dx prime rho x prime x minus x prime, where I'm assuming this x lies somewhere on this little cut here. Okay, then there's going to be contributions coming from this log cut here, okay, which is 2I log x minus a prime.
Then, question about that log cut.
Yes.
Even when you're in, so now you're writing the equation in finite volume, the exact equation for the.
Yeah, I'm writing the exact equation. Yeah, but I'm going to make. I haven't made the approximation yet.
So even in that case, you can really have these condensates.
Absolutely.
In space.
Right. Yes.
And so you really have these poles quite simple poles in your plasma.
Yes. Right. So now they're really there. So this picture is true even for J finite. Okay. But but the J very large, basically the assumption is these cuts become very short. Okay, that's what's going to happen. Okay, so this is a contribution from the log cut, and this will be the contribution from, say, the other square root branch cut on the other side of the giant magnon. And then I have a contribution from all the other ones. These all contribute to this. And then I have the right-hand side of the equation, which I'll split up. I'll split this up into the 2 pole terms, minus 2 pi times some integer n. Okay, so now I'm going to make an approximation. Okay, so since this thing is very short, okay, if I do these integrals along all these other integrals along here, so this one, this one, this one, this one, and this little bit here, okay, there's very little change in these integrals if I assume that instead of x varies a little bit along here, if I just assume that x is constant. Okay, so I can basically just assume that for this part, this term, this term and this term, okay, that these are constants, okay, when I'm doing this integral between a and b. Okay, so the only and actually this part too is basically also constant because a star is, you assume, is fairly far from a. Okay, so to a reasonable approximation then, instead of saying I have this integral equation, I have this integral equation. Okay, and the only thing I'm keeping that's x dependent is this log term x minus a that comes from the log cut, in particular the contribution near a. Everything else I'll just assume is a constant. Okay, and so the constant is basically every place I see an x, I'll just replace it by an a. Okay, because when x goes from a to b, it doesn't change very much. Okay. All right, so when I do that then say this term here, which is the contribution from all the other magnons, that's basically just going to be a log of some constants. Okay, and then I have the log. Then I have the log from this part. X I can pretty much assume as a constant. So I have a log of a minus a star. Then I have this term, and then I have this term, and this is also more or less constant. So what have I done? I basically reduced this problem to having a single cut. And single cuts are nice because single cuts give you sort of rational functions. Okay, they don't give me hyperelliptic functions. They give me rational functions. So I don't have to worry what's k and what's e. Okay, well, now I have to do a little, I have to solve this integral equation, assuming I have a constant, okay, and I've collaborated with several Russians, and so they all love this book, Mukshalashvili, and I even learned to pronounce it correctly, I think. And so Matthias knows this book very well, too. I misspelled it? Oh. What have I missed? Oh, there's the H, there's another H in there. I think I pronounced it right. What's that? Oh, I'm sorry. Okay. Well, if he sees it on the web, I apologize. So okay. So anyways, this book, you can find how to do an integral inverse Hilbert transform. Okay. So what do we? So basically, we have it's a two-cut. So we have a single cut. Okay. So we have cuts between a cut between the two branch points A and B, and what you do is you take the function that you're doing the inverse Hilbert transform for, and that function is this log function plus this constant. And then you divide by this function here, x minus x prime. Okay, and if you want to know more details about it, you can look in this book, which ask somebody else for the spelling. And you can solve this, equation. Now the thing about the constant is when you do an integral transform on a constant, it doesn't contribute. Okay, the integral transform on the inverse Hilbert transform on a constant is 0. Okay, so anyways, you can do this and you get rho in terms of arc cosines. Okay, but it's more convenient to just write x minus a in terms of rho. Okay, and x minus a is just equal to b minus a divided by 2 times this cosh of pi I rho plus 1. Okay, so let's check this. This makes sense. Okay, so at one endpoint, at one end of this cut, the density should be minus I, okay, because that's what's connecting to the log cut, okay, and in which case then this becomes the cosine of pi, so that's minus 1, that gives me 0, so x minus a is equal to 0, so that's x is at a. At the other point, the density should be 0, okay, the density of these goes to 0 at b, okay, if rho is 0, this is 1 plus 1, so that's 2, so it's b minus a, so that means x is at b. All right, so now we want to find this constant. Okay, well, to find the constant, basically what you do is you take this and you plug it back into the original integral equation. Okay, and the upshot of doing that is you find that b minus a, okay, is this term here. Okay, so it's 8 minus a IA. So I've written this in terms of an x naught, which is real, and some other term here, which is an a and b are not necessarily imaginary, but I've just written it this way. And then you get this product of terms coming from the other magnons. This product J corresponds to all the other magnons. And then you get this exponential term coming from the right-hand side of the integral equation. All right, so so let me just write this then as I times delta, where delta is real, times some phase, e to the I phi. And you can see that with this definition, that's I of b minus a. OK. So now with the resolvent, basically, okay, now that I have this density, basically, I can compute the resolvent. Okay, and well, you do that. And then once you have the resolvent, then you can find the various charges. So you can find Q, okay, which is given by this particular integral of the resolvent around around the cut. This should be O int there in your LaTeX file. And P is the integral of this divided by x. And E minus j, okay, which is what we're interested, is this integral of 1 plus g squared over x of this magnon, of this resolvent. Okay. All right, so let's now try and solve this then. So let a naught be x naught plus I a naught. So that's the endpoint of the log cut when j goes to infinity. Okay? So at that point, P is given by this. Q is given by this. Okay, and a naught you can write as a quarter of q plus the magnon energy, and x naught is a naught times the cotangent of p over 2. Okay, so now we have that expression. So what we want to do then is now we want to adjust a little bit, okay, when we go to finite size, such that p and q stay fixed. Okay. So to leading order, you can do this. Okay, so let me just leave everything in terms of this delta and the E phi for now, and then I'll go to the various cases later. Well, if you do this, you find that delta A has this very simple term. It's just minus I over 2 delta times E minus phi. Basically, what happens is that the log cut, the endpoints just split evenly about the end of this log cut. Okay, but unfortunately, when you compute delta E minus J, it's 0 to this order in little delta. Okay, so that means bad news. You have to go to the next order. Okay. Okay, so to the next order, then it turns out it doesn't have quite this nice expression, but you can still do it. It's delta x plus I delta A. Okay, so here's the leading order correction. Okay, so all I'm doing is taking this and writing it in terms of the real and imaginary parts. Okay, you get something that's order delta squared. It's a little messy, so let me not write it. But this part isn't so bad. Okay, you get g squared of cosine p minus 2 phi of this, delta squared. And you plug this in, and you find that delta E minus J is sine to the fourth p over 2 times this cosine of p minus 2 phi of g squared 4a naught squared divided by the energy of the magnon times delta squared. Okay, so this is the final result. And we can basically now just use what we found for delta and phi in various different examples. So let me do that. So various cases. Okay, so let's see if we can reproduce AFZ's result. So here is what delta E minus J is. It's this function here times delta squared. Now in this case, Q is equal to 0. So this is a classical charge. And there are no other magnons present. So you get delta e to the I phi is 8a naught e to the minus I pi n times the exponent of minus e divided by the energy of the magnon. Which we can write then, this E is equal to J plus the energy of the magnon. So we can write it like this, and we get this expression there. Good. OK, so we plug this in, and we find 16 sine fourth p over 2, g squared e over m, e to the minus 2j e m. So I pulled out this e m divided by e m and wrote it as a 1 over e squared. And we get this expression here. Now, so as Sergey was pointing out, what do I do when p is not equal to 0? Because you notice that I get from from choosing the branch cut, I get this factor of 2 pi n. And so this seems like this makes no contribution whatsoever. Okay, but this 2 pi n is not there, and so I should have a cosine p factor. But that, of course, is not what they got. They got everything except this term in red. So if n is an integer, then this does not agree with AFZ. Okay, but it's probably what I did was illegal. Okay, I'm not allowed to just have a single magnon. Or perhaps what I can do, and I'm not actually positive about this, but I think it's probably true, that choosing, if I'm allowed to choose some non-integer value of n, okay, this is probably the same as introducing this e to the IP factor in AFZ. And so this then would cancel off this p there and give me what they got. But in any case, I'm not gonna dwell on that.
What is the right number?
It's the along this little cut here. That's n. So it seems like n doesn't matter.
If you think in terms of the sphere S3.
I'm sorry, what?
If you think in terms of classical solutions. S3. What if n is the right number along the second angle?
I
have two angles.
I don't think it's that actually. Somehow it's some momentum. I think I think actually it turns out not to. It's not related. It's not related to the difference in the ends along when I recut the surface, because it seems that in the end you're going to see that it doesn't matter what it is. Okay, because I'm always going to get a 2 pi times an n. Well, it will matter a little bit, but at one point. Okay, so anyways, that was the case where Q is equal to 0. Now let's go to one magnon where Q is not equal to 0. And in this case, then, we have a delta that looks like this, okay, where it's the energy of the magnon divided by this term I call ES squared. And ES squared is not quite the energy of the magnon squared. It turns out it's Q squared divided by sine squared P over 2 plus 16 G squared sine squared P over 2. So there's this extra sine squared term here. So it's not quite the energy squared of the magnon. Well, if I plug this term back in, okay, you have delta E minus J. And so what happens then, if I choose to write it in this expression where I break up the energy into parts, I have the e to the minus 2j e to the m divided by es squared. Okay. Then I get the sine fourth p of 2. But I also have this cosine function, p minus 2 of some phase. But now the phase is, in the case of q equals 0, this term was 0 because this is multiplying by q. But there's this extra phase there as well, minus pi over n. Okay, and this is added to this momentum p. Okay, and then this alpha. Okay, so this alpha shows up in this e to the 2 alpha. It's no longer e squared because of the fact that you're not dividing by the energy of the magnon now. You're dividing by something slightly different. So this thing gets modified. So, anyways, so we have this other phase. Okay, and this other phase is you're going to notice is highly oscillatory. Okay, because e is assumed to be a very big number. Okay, and in fact, e should be much bigger than es squared divided by q. Okay, so we assume that this is a very big number. Okay, so changing the momentum a little bit will change this phase. Okay, so the direction in which the energy changes will depend a lot on what the momentum is. What else? Okay, so let me also say that it might not be the best way to express things in terms of e to the 2 alpha. It's much more, you can basically get rid of this e to the 2 alpha by just replacing this j by the total energy. Okay, so it might be a more natural thing to do. Yes?
Why do you call this one magnon?
One bound magnon, I should say. Okay.
It's bound state of
Bound state of Q magnons, but one big bound magnon. Okay. Yeah, that's right. So now let's go to the case where I have several magnons, and let's assume that Q is equal to 0. Now, in this case, everything's almost the same as what I had before. The only difference now is I have this product term here, which comes from the positions of the different the ends of the log cuts for the different magnons. Okay, now it turns out then that the energy, so the energy of these different magnons is 4g times sine of pj over 2. And in the case where this q is equal to 0, it turns out that this thing simplifies quite nicely. Okay, it turns out that this is just the exponent of minus I times the sum of all the other momenta divided by 2. Okay, and then I have this sine of pj plus pk over 4 divided by the sine of pj minus pk over 4. And this is assuming that the momentum is between 0 and 2 pi. Otherwise, if I don't assume that, then I have to change some of these signs to cosines and things like that. So let's just change that. In the end, okay, won't matter. So with this extra term then, the only thing that happens from the original result, okay, is that we're going to get this thing squared. And now we have this extra term in the phase. Okay, so the total phase then, remember it was p minus 2 phi. Okay, so the total phase now is cosine of the sum of all the momenta. And these are physical. So if I choose the moment, this is a physical string. So the sum of the momenta have to be 2 pi. Then this cosine goes away. Okay. So then I get the main result then is that I get a result that looks like the finite magnet. I can get rid of this e to the 2 alpha j term here just by changing this j to an energy. Okay. And the main upshot then is that I just get this extra factor here. So it's just the sine squared of the different of pj plus pk over 4 divided by this. Okay, so a few comments. Okay, now the pj's should be quantized since you're putting it on some finite size. So I'm not going to say much about this, but I'm assuming that the way I'm choosing those momenta is that the momenta are properly quantized in this case. So I can always start at the j infinity limit and choose the momentum such that they will be the right momentum for finite j. Second thing, magnons come in flavors. Okay? So even though I'm calling this q equals 0, the true giant magnon has a charge of q equal 1. Okay? And this q equals 1 comes from the fermion zero modes on each of the magnons. Okay? So there's 8 fermion zero modes, and so that will lead to 16 different. 16 different types of giant magnons based on these different flavors. Okay, but I'm doing a classical calculation here. Okay, so the flavors basically don't show up. Okay, so at least at this level. Okay, so a conjecture, and then I decided it's not really close to calling it a conjecture. It's probably more of a guess, maybe an educated guess. But the flavor effects are subleading in 1 over g. Okay, that seems to, maybe that might be right. Okay. Okay. So then we could ask what happens as the momentum, say one of these momentum, approaches another momentum. Because you notice that this thing will become singular at this point. Okay, so in that case, then this thing breaks down. So basically what we're doing, say, is we consider the case then where all the magnons basically end up on top of each other. Okay, so basically the m magnons with the same momentum and q. So let's go back to our original integral equation. And we just have to modify it a little bit. Okay, so we have m total magnons. So that means that we're going to multiply this thing by a factor of m. This log term is the same. And then this constant changes a little bit. So I'll put a cm here. And the difference is because it sees there's m of these things. So it sees all these different m copies of these log cuts. So we get that term there. But the rest of these expressions are the same. So the solution is basically exactly the same as the single magnon case, except we just have to do a few things. Okay, we just have to divide the energy by m. We have to divide j by m. And we have to divide this phase by m. Okay, so we do that. And we get sine to the 4th p over 2 cosine p minus 2 phi over m, g squared e to the 2 alpha. Okay, now this alpha can go, it will basically be, this alpha will basically be 1 if q is equal to 0. And then we have j divided by m, e over m, es squared. Okay, and now the main thing is that we get exactly the same thing we had before for the single magnon case. Okay, except j gets divided by m. Okay, this is just the e squared here, but so does n. Okay, so n gets divided by m. So a physical string would have the momentum. Okay, turns out to be, if we have say just these m giant magnons. Okay, then the physical string would have to be 2 pi times some integer divided by m, so that the total momentum is an integer times 2 pi. So we can basically choose this integer n to get rid of this p factor right here. So this basically then would reproduce AFZ's result for these special momenta, or the overflow results of Stelfi and Farini and Grignani and Semenoff. And this would correspond to, say, the GKP limit if we just have 2 magnons, or these multi-cusp generalizations by Martin Krushenski. All right, so I have 12 minutes, more or less. Okay, so all right, so well, we thought our results were pretty simple, didn't look too complicated, so we were trying to think of ways to check it. And one way you can check this is you can basically go back to the Heisenberg model. So you can do that by letting this charge q be much bigger than g. So g will still be very big, okay? But if we make q much bigger than g, then we should approach the Heisenberg limit. Okay, so recall then that the energy of this magnon then is q plus 8g squared over q sine squared p over 2. And when we take these limits, basically what happens to this delta E minus J is that this becomes sine to the fourth P over 2 G squared over Q X. This factor here, this is the energy. This was the energy. Now it's J plus Q basically to this order. And then we have a sine squared P over 2 divided by Q. We also have a phase, which is highly oscillatory. And yeah, we write that basically as J plus Q like that. All right, so the question then is how do finite size corrections appear in the beta equations? Okay, so what happens then when we have these cuts, okay, these log cuts, when we go back to the beta equations, these log cuts become these beta strings. Okay, so these are separated by i's along here, and these become these beta strings. Okay, so they're separated by I. And let me just remind you about how we get this separation of I from the beta equations. Okay, so we're assuming that J goes to infinity. So that means that this exponent is infinite. Now, if the imaginary part of u is greater than 0, then it means that the modulus of this term inside here is greater than 1. Okay? So that means that this term on the left-hand side is infinite. So to compensate for that, on the right-hand side, we need to get an infinity. Okay? And the way that you get an infinity is if you have one root at uj, then you put another root such that uj minus uj plus 1 approaches I, then this term down here in the denominator is going to 0, and so this thing is becoming singular. So let me call u1 the root at the top here. Okay? And if I have q of these things, okay, then this position of this thing is x naught, where x naught is some real thing, which will depend on the momentum, and the imaginary part is iq minus 1 over 2, okay, as j goes to infinity. All right, now let's assume j is not quite infinite, but still very large. Okay, so it should be then that u1 minus u2, okay, is equal to, well, actually I'm missing an I here. It should be I plus some I times some very small bit epsilon here. Okay, so this would be very large, okay, with u1 with the imaginary part. So the imaginary part is greater than 0. So this is very large. Okay, so to compensate it, u2, which is the next root down, has to differ from u1 by I times I epsilon, plus I epsilon. Now let's go to u2. Okay, so u2, the imaginary part, if q is still very big, okay, the modulus is more or less the same as what I had for u1. Okay, but so the term on the left-hand side is also going to be very large. So to compensate, we need something very large on the left-hand side. But we already have a term in the numerator, which is u2 minus u1 plus I. And this term in the numerator is going to 0 as epsilon goes to 0. So to compensate, we need something in the denominator that goes to 0 even faster. Okay? So it means that u2 minus u3 basically has to go as I to the epsilon squared. Okay? And we can continue down through here, and these positions of these roots get closer and closer to the value they have in the j goes to infinity limit. Now, when we go down below here, what happens is that then they start spreading out a little bit. But basically, all of the action, okay, is all concentrated in this top root and this bottom root, at least to the order of the approximation we're doing. Okay? So that's just like in the finite gap. Remember, we had this very long log string, this very long log cut, and we had a little tail at the end. And we're solving the equations around this little tail that gave us our corrections. So it's the same story here, is solving what happens to this top root and this bottom root will give us our equations. Okay, so let's solve this. Okay, so let's take the top root so it turns out if we put this into the momentum, okay, this is x naught plus iq. These should be divided by 2's here. Well, the q should be divided by 2's. Okay, and then on the right-hand side, we get, if you go back, okay, so from these terms, okay, so from the separation between here and here is I. So this term will give me a 2I, and this term will be I epsilon. The next one will be 3I and 3I and I, etc. So if we go, you're going to get, on the numerator, we're going to get 2 times 3 all the way up to q. And on the denominator, we're going to get epsilon times 1 times 2 all the way up to q minus 2. And with q squared over epsilon. So I'm just considering the case of a single magnon, a bound magnon. Okay, but this can be generalized to having more of them. But for the lack of time, let me just do this. Okay, well, we can solve this for this epsilon. And it turns out then this epsilon is roughly q squared of e to the minus 2l sine squared. This should be, I didn't put the frac in right. P over 2 q divided by q times this phase e to the 2I phi, where this phase is L2q sine p over 2. And if you go back and look at our finite gap results, you see that this epsilon is proportional to delta squared times e to the 2I phi. So in this case, we just have to do a first order computation. Okay, so it's a little simpler. Okay, the other case we had to go to second order. Okay, but it turns out the leading order correction is of order delta squared. Okay, well, you do this. Okay, so you have to, the momentum will change a little bit, so you have to adjust the position of the real value here so that the momentum stays fixed. Okay, you do that. Then you find the change in the energy. The energy changes a little bit because you have delta, you have an I epsilon. And what you do is you adjust this x such that delta p is equal to 0. And you find that delta E minus j is given by this. It's the same result. Well, of course, it's the same result because I just dropped and dragged it from the other page. But it turns out it really is the same result. Okay, and so it matches with that, including the t minus phi a. Okay, so in my remaining 5 minutes, let me just talk about some preliminary stuff in using the thermodynamic beta ansatz. So there's been some very nice papers on this. Sort of the first one applied to this problem is by Ambjørn, Janek, and Christensen. And then more recently, there's Janek and Lukowski and Aritunov and Frolov. So we would like to sort of apply, especially these results of Janek and Lukowski, to the case of having more than one problem. Okay, now for more than one magnon, this turns out to be a very hard problem. In fact, if you go look in Lucer's paper, he didn't really solve the problem because it turns out that there's other corrections that were bigger anyway, so he didn't worry about it. Moreover, as you saw in the talk yesterday, there are flavor indices along this. Okay, so you have to worry about those. So in particular, so in the case, remember, if we just had one magnon, we had what enters into the problem is the S matrix for 2 magnon scattering. Okay, if we have 2 magnons, we're going to have the S matrix for 3 magnon scattering. And even though it's integrable, it's factorizable, okay, it's still probably not so nice. So if we have more than magnons, it'll be even more than 3. Okay, so I'm only going to do one slight thing in this, and that is to try and just find the exponential term for Q-bound magnons. Okay, there I used bound correct. Okay, so as Ramil was telling us yesterday, there's sort of 2 types of terms that can contribute in this case. We have what's known as the mu term, okay, and this F term. And the mu term is a case where the magnon's coming along and it splits up into these on-shell particles, and then it rejoins and keeps going like this. And now these things have charges, okay, and the charge of this is Q. In order to conserve the charge, then I have to have Q minus N going along here and N along here.
Particles that appear in the intermediate state don't have to be in the SU2 sector, right?
They don't, but, and I'm not really assuming that, but so they're,
But you see, these
classical
quantum numbers are actually non-abelian quantum numbers.
No,
So it's there are many states.
Sure. In fact, yeah, they don't actually have to add up. In particular, yeah. But they can, right. So this could add, I could add, but I think I can only change it by 1, or I can change these by ones. Okay, so it's not going to matter. And in fact, in the case of the single magnons, they didn't add up, right? Because it was 1, 1, and 1.
Yes.
Right. But in this case, I can more or less assume that and it turns out this will be dominant. Okay, assuming they do that. That's a good point. Yes. In fact, yeah. Okay. So, anyways, so I have a creation and annihilation of basically these odd-shell particles with charge Q and Q minus N. And so, as Ramil was saying yesterday, we expect some exponent of I to the PC times J, where PC is the momentum of one of these virtual particles. Okay, so in order to have energy conservation and momentum conservation, this would be the energy of this giant magnon, the incoming giant magnon, and it should be equal to the energies of these other giant magnons. Okay, so there's one with charge Q minus N, there's another with charge N, and the momentum of this first one we'll say is P plus delta P, and the momentum of this other one is minus delta P, but that's just delta P there since it's sine squared. Okay, so you can solve this to leading order in delta P, okay, and you end up with this quadratic equation, and what you find is delta P is given by this, which is precisely the exponential terms we had before. Okay, where this part here is the exponentially suppressed term. This is the imaginary part, and you choose this depending on the sign of n. Okay, if plus or minus I n I, and this was the phase we got there. So you also get that phase as well. Now there are different choices for n, and basically we want to choose the n such that we get the dominant contribution, and the dominant contribution is making this imaginary part as small as possible, and so that means n should be plus or minus 1. So I should say it matches the result once I choose n to be 1. And so as Nick was saying, it's possible also to have them not quite conserved because these are non-abelian, but it turns out that those are subleading as well. I didn't show that here. Okay, so let me just finish. So we found these leading order finite size corrections for basically an arbitrary number of giant magnons. We could also do the case of arbitrary bound case of giant magnons, but the expressions don't look quite as nice. And the leading order has a relatively simple expression, especially if all magnons have Q equals 0, classical charge Q equals 0. So the next two leading orders can be found, okay, basically systematically, okay, just like you can integral equations, you can expand systematically, but it's probably very tedious. On the other hand, you might be able to go right to some hyperelliptic functions and find some nice stuff. I don't know. We can compare this with other methods. Okay, so there's some work being done by Thomas and Tristan. Well, I don't know, two peer. I should maybe work in progress. I don't know. Where they're analyzing two solitons in the Sine-Gordon model. And I might just say that since the result seems relatively simple, I think there's some hope for finding these prefactors using these methods of Janik and Lukowski that we heard about yesterday. And my guess is that, so for example, the contribution, this mysterious factor of 8 over e squared, well, I don't know what's going to happen, but the fact that it doesn't seem to depend on the flavors, I think that, say, in the Janik and Lukowski analysis, it turns out that when you have to go to these singular points in the next to leading in the corrections to the phase factor. Okay, and I have a feeling that the phase factors don't matter in that part, but I don't know. That's a guess. Okay, well, thank you for your.
So the correction is always proportional to e to the minus the energy divided by
This it's
by sine e over 2, something like that.
yeah, it's e to the minus 2 times the energy times the energy of magnon divided by this es squared term, where this es squared is this. So that's the generalization for the bound ones. Okay.
And E is the total energy.
E is the total energy, so all the contributions from all the other magnons.
This valid for many
Yeah.
ionic giant magnons.
Yeah, many. Yeah, well, not J by magnons, but if a number that is much smaller than J.
So do you think you can generalize this for SL2 sector?
I was wondering that, but I don't know.
So, well, how would the next order, the next correction look? I mean, what's it?
Well, I imagine it'd be e to the minus 4e times this, but I don't know. I can't.
Higher powers, the exponential down.
Yeah, so the next term I think would be e to the minus 4e, I would guess, times this same factor.
Have you seen appendix paper? Giant magnon, finite size correction.
Yeah, no, in the appendix I remember you boosted to q equals 0, but you didn't boost. I thought you only boosted the actual energy and not the finite size correction.
No, we have equation for finite J.
You do?
Yeah.
Because I what? Because I
we have equations, but we didn't analyze the equations.
Okay.
But it's possible to analyze them.
Oh, okay, good. All right. I remember. Okay, so in the appendix you also had boosting, right? I remember that part. Okay, I'll have to go look at it.
And there was some. Well, okay.
Okay, I'll look.
Let's show another.